So this one is called the Spearman rank correlation. The Spearman rank correlation. So we've had correlation coefficients before. It's a similar one. We're talking about the correlation between two things. However, it's not linear because we are talking about rank. Look at the name. It says Spearman rank correlation. So we're trying to figure out, is there a correlation between ranks? So we're going to learn about what are called monotone relations. Maybe I should say we're going to learn about monotone relations. That's supposed to be a joke. So we're going to learn about monotone relations in the Spearman rank correlation coefficient, computing that Spearman correlation coefficient, and then we're going to conduct a statistical test for the significance and interpret the results in the context of the application. Data that is given in ranked form is ordinal type. That goes way back. We talked about this yesterday. It goes way back to when we learned about the different levels of measurement. I believe that was Unit 1 when we were learning kind of the foundations. So data that's given in the ranked form, the ordinal type, are different from data given in measurement form, like the interval or the ratio type. For instance, if we compared the test performance of 3 students and say Elizabeth did the best, Joel did the next best, and Sally did the worst. Poor dumb Sally. We are giving the information in ranked form. One did better than the other. We cannot say how much better Elizabeth did than Sally or Joel, but we do know how the 3 scores compare. So we can't say that, well, Sally scored 25 points less than Joel. We don't know that because we're using the ranks. If the actual test scores for the 3 tests were given, then we would have the data in measurement form and could tell exactly how much better Elizabeth did than Joel or Sally. We studied linear correlation of data in measurement form. In this section, we will study correlation of data in ranked form. As a specific example of a situation in which we might want to compare ranked data from 2 sources, consider the following. Hendrix College has a new faculty position in its political science department. A national search to fill this position has resulted in a large number of qualified candidates. The political science faculty reserved the right to make the final hiring decision. However, the faculty is interested in comparing its opinion with the students' opinion. So those are the 2 ranks that you're going to compare. How did the students rank these candidates compared to how did the faculty rank those candidates, and to see is there any correlation between those 2 things? Y'all with me?
Yep. Sort of.
A random sample of 9 equally qualified candidates were asked to give a classroom presentation to a large class of students. Both faculty and students attended the lectures. My very first interview that I had for a teaching position was this scenario. I had to teach a lesson. It was at Zeeland Public Schools, and thank God I didn't get it because I wouldn't be here, and I love this place. So Zeeland is where it was, and they put me in front of a classroom. The teacher stepped aside. There was a panel of people, principals, assistant principals. There were a couple parents that were on the committee. They had a student or 2, if I remember right, that were on the committee. But then they had a whole live student body, a classroom. And the teacher just stepped aside, and I taught the lesson that they told me that, they had sent me and said, well, this is what you're going to teach. Okay. So I did that. So I'm sure that they did a test like this where they compared the ranks of what the students thought and what the committee thought. So at the end of each lecture, both faculty and students filled out a questionnaire about the teaching performance of the candidate. Based on these questionnaires, each candidate was given an overall rank from the faculty and an overall rank from the students. The results are shown here. So you got the 9 candidates. You can see how the faculty has ranked each candidate. And again, it's a rank. It's not like, well, this person scored this and this person scored this. It's just how they fared against the other people. And then you can see how the students rank them.
Is that the average of the students? Or is it just like
They would take the scores of the students. So maybe you said, well, candidate 1 you gave him like a 60% and Brant gave him a 75%. They would average everybody's scores for all the students' scores for the candidates, and then they would, based on that average, they would rank them as to who had the best average, who had the second best average, the third best average, and that's how they came up with those ranks. Okay. Using the data in ranked form, we answer the following questions. Do the candidates getting higher ranks from the faculty tend to get higher ranks from the students? Is there any relation between the faculty rankings and the student rankings? And do the candidates that get higher ranks from faculty tend to get lower ranks from students? And you're like, whoa, what's the difference between the 1 and 3? The first one says the faculty get higher ranks, and the students get higher ranks. Number 3 says do the faculty give higher ranks and the students give lower ranks. This is going to be that monotone correlation or monotone relationship. So is there any relation between the faculty rankings and the student rankings is really what we're testing. We will use what is called the Spearman rank correlation to answer such questions. In the early 1900s, Charles Spearman of the University of London, that was my bad British accent, London. Yeah, it's not good. He developed the techniques that now bear his name. The Spearman test of rank correlation requires us to use ranked variables. Because we are using only ranks, we cannot use the Spearman test to check for the existence of a linear relationship between the variables, as we did with the Pearson correlation coefficient. The Spearman test checks only for the existence of a monotone relationship between the variables. Okay? Now here in the next slide, maybe I should do the next slide. The next slide talks about this. It says that the relationship between the variables x and y. So in our example, the relationship between the faculty ranks and the student ranks. There is a monotone relationship if, as the x increases, as one variable increases, then the other is constantly increasing. Not necessarily at the same rate, but it's generally increasing. Or, as one variable is increasing, the other one is consistently decreasing. So if we go back here, the first one here, A, is a monotone increasing. As x is increasing, so as x is getting bigger, the y is consistently getting bigger, obviously, because it's a positive linear correlation. But let's look at C. As x is getting bigger, the y value is consistently getting bigger. Not at the constant rate like a linear relationship has, but it is generally getting bigger. They've got this all mucked up. This is a monotone decreasing because as x is getting bigger, the y is getting smaller. So this slide, B and C, the text should be switched here. No. Yes, the text should be switched here. Sorry, I got hung up on the graph. So C actually is a monotone increasing. B should be a monotone decreasing. And D is a non-monotone because as x is getting bigger, here, y initially starts to get smaller, but then at some point it then starts to increase again. It has to be constantly decreasing or constantly increasing as x is getting larger. I pause for reflection. Let that soak in. Okay? Must always be increasing or always decreasing. In a non-monotone relationship, as x increases, y sometimes increases and then sometimes decreases, or it stays unchanged. Before we complete the solution of our problem about the political science department at Hendrix College, we need the following information. Suppose that we have a sample size of n of randomly obtained ordered pairs x, y, where both x and y values are from ranked variables. So very much like the political science question here, x was how the faculty ranked, y is how the students ranked. And so if you had an x, y, 3, 4, that would mean that the faculty ranked them third and the student ranked them fourth, but it's from ranked variables. If there are no ties in the ranks, then the Pearson product moment correlation coefficient can be reduced to a simpler equation. The new equation produces what is called the Spearman rank correlation coefficient, which is denoted by R sub S. When I see R sub S, I'm just going to call it the Spearman rank. The Spearman rank correlation coefficient can be computed by doing 1 minus 6 times the sum of the differences squared. So you see this D, that is the difference in the X and the Y's, the difference in the ranks, as you're going to see. So you add up all of the differences squared. Remember why we square them is because the differences, some of them might be positive, some of them might be negative. When you add them, you don't want them to just be 0. So you have that divided by N, which would be the sample size, times the quantity N squared minus 1. The Spearman rank correlation coefficient has the following properties. You are always going to have values that are somewhere between -1 and 1. And just like the Pearson correlation coefficient, as that number is closer to 1 or -1, the stronger the relationship is. The stronger that monotone relationship is. So the closer that the Spearman rank is to 0, the less relationship there is between the two variables. The probability distribution of the Spearman rank depends on the sample size. It is symmetric about this, the Spearman rank of 0. So we're going to have Table 9 of Appendix 2. Y'all have red folders, yes? Find Table 9 of Appendix 2. Okay, this is going to give critical values for certain specified one-tail and two-tail areas. Use of the table requires no assumptions that X and Y are normally distributed because this is a non-parametric test. We don't need to know about what the distribution of our values is. In addition, we make no assumption that X and Y, the relationship is being linear. The Spearman correlation coefficient is the sample estimate for the population Spearman rank correlation coefficient. The population correlation coefficient is P sub S. P sub S would be the population Spearman rank correlation coefficient as opposed to the R sub S, which is a sample. We construct a test of significance for the Spearman rank correlation coefficient in much the same way that we tested the Pearson correlation coefficient. The null hypothesis states that there is no monotone relation between X and Y. So that means that the population rank correlation coefficient, the P sub S, is 0 because there's no correlation between the two. The alternate hypothesis is either that rank is less than 0, bigger than 0, or it's not equal to 0, and that tells us whether we do a left tail, right tail, or two-tailed test. A left-tailed alternate hypothesis claims that there is a monotone decreasing relation between X and Y. A right-tailed alternate hypothesis claims that there is a monotone increasing relation because it's positive. Positive means as X is increasing, Y is increasing. If that correlation was negative, then it's a decreasing relationship. As X gets bigger, Y is getting smaller. Okay, so then you have the whole left-tailed, right-tailed tests like we've done before. So here is the information related to the Hendrix College. So we had the ranks of the faculty, we had the student ranks. We have a separate column that calculates the difference between the ranks. And the difference is found by doing X minus Y. So the candidate number 1, we would take 3 minus 5, and we'd come up with a difference of -2. We then have to square that difference so that we can add them together and they don't cancel out. So that you have the D squareds and then you have the sum of D squared. So you add up all of those differences, those squared differences, and you get 16. So now we're going to go find and do this test. Using a 1% level of significance, we're going to test the claim that the faculty and student tend to agree about a candidate's teaching ability. This means that x and y variables should be monotone increasing. Should be monotone increasing, that they're in line with each other. Since the population Spearman rank is, or P sub S is the population Spearman rank correlation coefficient, the null is that it is 0, that there is no monotone relation, and our alternate is going to be that it is positive, so it's greater than 0, that there is some sort of monotone increasing relationship. So we compute the sample test statistic, which is compute the Spearman rank correlation coefficient for the sample. So here's the formula. It's plugged in the values. We added up the d squareds. That was 16. We multiply by 6 because that's just part of our formula. We had 9 candidates times the quantity 9 squared, which is 81 minus 1. We come up with 0.867. So if we look at table 9. My nose is really itchy. Table 9. Appendix. How do you get rid of this thing over here now?
You don't.
Man. So annoying.
Not good at settings,
All right. So what we're looking for is the Spearman rank correlation coefficient for the sample was 0.8 something, right? 0.8. What was it?
Numbers.
0.867. So we have to look to find our sample size, and just like we've done in all of these other tasks, we've done 1,000 of them by now, is we're looking for where does 0.867 fall. And so you can see it falls right in between the last two, this 0.834 and 0.917. Since we are doing a one-tailed test, we go up to the top and we say, okay, 0.005 and 0.001. Some of you are still struggling on how to write your interval. You're mixing them up. Some of you are doing this. 0.005 is less than the p-value, is less than 0.001. 0.005 is bigger. Isn't that backwards?
Yeah.
0.001, that value is smaller than our p-value. If we read that backwards, it says that our p-value is bigger than 0.001. We know that it's bigger than 0.001. And so make sure that this goes smallest to largest every time you write that interval if you're using less thans. So we know our interval is somewhere between 0.001 and 0.005, so we can then compare that to our level of significance, which was, it was 1%, was it? Yeah, we compare it to our alpha 0.01, and we see that at the 1% level of significance, we conclude that the relation between faculty and student ratings is monotone increasing. We reject the null. The null was that population Spearman rank was 0. It is not. It is positive. This means that the faculty and students tend to rank the teaching performance of candidates in similar ways. Higher student ratings of a candidate correspond with higher faculty ratings of the same candidate. There is the context of the problem. That's interpreting what was all that work about. What does that do for us? So there's the things we just went through, and that's it.